Hello everyone, welcome to Physics 1. My name is Duane Hamacher. I'm an associate professor here in the School of Physics at the University of Melbourne. I'm going to be your instructor for the first half of the semester, where we're going to talk about all things related to mechanics, kinematics, and dynamics. I'm originally from the United States, and I completed my undergraduate degree in physics at the University of Missouri. I did my master's degree in astrophysics at UNSW. By research, I spent a couple of years up at Siding Spring Observatory looking for planets transiting their host stars. I then went to Macquarie University, where I completed a PhD at the intersection of astronomy, science, and culture with respect to Aboriginal Australians. I'm recording this video at the Parkville campus of the University of Melbourne. I am sitting on Wurundjeri land. Wurundjeri are the traditional owners and custodians of this land. They're of the Kulin Nation, and I pay my respects to elders past and present. It's important that we remember that Aboriginal and Torres Strait Islander people were the world's first astronomers and the world's first physicists. Technologies developed by Aboriginal people over tens of millennia have utilized concepts of celestial mechanics, aerodynamics, fluid dynamics, and a lot of other areas of physics that don't often get credited the way they should. So I'm going to try to include some examples of that throughout our lectures the first half of this semester. Physics itself is the study of matter and energy. And we're going to be looking at this as a fundamental science throughout the semester. We're going to cover topics in relativity, waves, optics, and mechanics. The assessments for this subject are broken up between homework assessments, laboratory assessments, and a final exam. Your final exam is actually weighted pretty heavily. It's worth 60% of your final grade. 25% of your total grade are the labs, and the rest is split up between various homework assessments. You must complete and submit 80% of all of your labs in order to pass this course. For this subject, we're going to use the Fundamentals of Physics by Halliday and Resnick. This is the 11th volume of the text. For the first 6 weeks of the subject, we are going to discuss all things related to mechanics. This includes motion and vectors, force and Newton's laws of motion, energy, work, and power, rotational motion, and angular momentum. Well, what do all these things have in common? We can see that they're all based on different concepts of relativity. Galilean relativity, developed around 1632, shows us that the laws of mechanics are independent of the speed of the laboratory in which they are measured. In 1905, Albert Einstein developed special relativity. This shows us that the laws of motion are independent of the speed of the laboratory in which they are measured, and the speed of light is a constant for all observers in all frames of reference. In 1915, Einstein developed the general theory of relativity, which looks at objects in a gravitational field. We see that the laws of physics in an accelerating laboratory are the same as for those in a gravitational field. Special relativity deals with a constant velocity. General relativity deals with acceleration or change in velocity.
No doubt you've heard that there are two theories of relativity: the special theory of relativity and the general theory of relativity. So naturally you want to know, what's the difference between them? Well, here's how it goes. Einstein was obsessed with understanding how the world, how the universe would look to someone who's moving through the universe. You wouldn't think that that would be the key to understanding reality, but it turns out that it's a vital question to ask. Now, in the special theory of relativity, Einstein focused on observers that were moving with a very special kind of motion, constant velocity motion. That means motion at a fixed speed in a fixed direction. Now, even with that restriction to that special kind of motion, Einstein realized that you could extract some deep insights into the nature of reality. He was able to figure out that at constant velocity motion, an object would be squeezed. It would be compressed along the direction of that motion. And if you want a more realistic version of that, you can have a taxi cab moving down Fifth Avenue, going at very high speeds. That taxi cab would appear to be compressed along the direction in which it's moving. And in fact, if you were to jump in to that taxi cab, Einstein's insights tell us that the outside world would undergo some really wild-looking distortions because of the impact of constant velocity motion on space and on time. Deep insight. Now, that was 1905 when Einstein came up with these ideas. 10 more years of working and thinking and calculating allowed him to generalize this theory to motion that was not constant velocity motion, motion in which the observer could be speeding up or slowing down or going around a bend, what we call accelerated motion. And it's not obvious, but that move from constant velocity motion to accelerated motion, it turns out brings in an understanding of the force of gravity. So Einstein realized that by now including generalized motion, that would include accelerated motion, he could get an understanding of the force of gravity in terms of warps and curves in the fabric of space and time. One of the most beautiful insights ever. So in a nutshell, that's the difference between the two theories. Special relativity focuses on motion at constant velocity. General relativity generalizes that to include motion that can be speeding up or slowing down, accelerated motion, and in so doing, it turns out, brings into the theory an understanding of the force of gravity.
Now, these laws are only valid for speeds very, very much below the speed of light. Once we get to speeds close to the speed of light, or relativistic speeds, things change. Physics and engineering are based on the precise measurement of physical quantities. In order to do this, we need rules for measurement, and we need standard units for measurement. A unit is the unique name assigned to the measure of a quantity. There are 7 fundamental quantities, but only 3 relate to our base units in mechanics. That's length, time, and mass. All of these have been assigned standards, and all of these are used to define other physical quantities. Now, prior to May of 2019, the history of physics shows us all different sorts of standards for how we go to define different units of measurements.
Our home. We've come so far. But how did we get here? Measurements. As humans, we learned how to measure before we learned to write. Through measurement, we learned to count. We used the sun to tell time and based units of length and weight on other earthly objects. Measurements helped us to become merchants, builders, astronomers, navigators, engineers, and scientists. The need for better measurements grew with each invention. With the adoption of standardized measurements, we created the global economy. Today, we have reached a pivotal point for humanity. We no longer have to rely on physical objects for precision measurements. The rules of nature operate smoothly from the invisible quantum world to the far reaches of the universe. And so should our measurements. For the first time, all of the world's measurement units will be accurately defined by nature's fundamental laws. In 2018, the world science community came together at Versailles to advance measurement science for generations to come. Anyone, anywhere, will now be able to precisely measure mass, temperature, electrical current, and amount of substance just as accurately as we already measure time and distance. We've come so far, and if history is any indication of the future, our new measurements will take us further than we have ever imagined.
What is a kilogram? How do you measure a meter? How do you define a second? Over time, these have changed from actual artifacts, from physical things in a lab or in an institution, to concepts where we base them off of principles like the speed of light.
On November 16th, representatives from nearly 60 nations will be meeting in Versailles, France, to vote to change the definition of a kilogram. Not only that, they will also be changing the fundamental unit of temperature, the Kelvin, the unit for amount of substance, the mole, and the unit for electric current, the ampere. That is 4 of the 7 base SI units in one day. And after that, all SI units will be based on fundamental constants of nature and not physical artifacts. The kilogram is the last base SI unit to be defined by a physical object. Since 1799, 1 kilogram has been defined as exactly the mass of a single metal cylinder stored in Paris. It was swapped out once in 1889. But this international prototype kilogram, or Big K as it's affectionately known, has problems. I mean, weighing it with, in theory, identical cylinders, scientists have found that their masses are diverging, so it doesn't even seem to maintain its mass. Plus, it's really hard to get access to Big K, and that makes using this definition really difficult. So how do you create a mass standard that will never change and also be available to everyone, everywhere? Well, the solution is you set Planck's constant to have a fixed, exact value. Now, I know that sounds a little strange, so bear with me for a moment. I mean, Planck's constant is best known for relating the frequency of a photon, a particle of light, to its energy. But we also know that energy and mass are related through E equals mc squared. So hopefully you can see how Planck's constant is involved in mass. But the problem, as it stands today, as I'm recording this video, is that Planck's constant has some uncertainty. I mean, we know the value of Planck's constant to a large number of decimal places, but those last couple of digits, they're actually uncertain. What is certain is the mass of that platinum iridium cylinder stored in a climate-controlled vault in a basement in Paris. It is exactly 1 kilogram, no uncertainty. So the solution is to flip this on its head. Set Planck's constant to have an exact fixed value, and then that cylinder in Paris will no longer be exactly 1 kilogram. I mean, it'll be a kilogram, but not exactly. The thing that is now exact is Planck's constant, which determines how big a kilogram is. But if you're gonna fix the value of Planck's constant, well, you better get that value right so that it's consistent with all of our current measurements and all of the masses that exist in the world right now. And so for the last several years, scientists around the world have used multiple different techniques to try to measure Planck's constant as accurately as they possibly can. One of the major methods was using a watt balance, where essentially they balance the weight of a kilogram with the force from an electromagnet. If you want more detail, you should check out my video on that topic. Scientists also created arguably the roundest object in the world, made of one type of silicon atoms. These methods have been complementary because now they're able to compare all of their different findings from physics and from this more chemistry method of Avogadro's constant and determine what Planck's constant really should be. So if the vote goes well, the future definition of Planck's constant will be that it is exactly this number. Planck's constant is fixed. That cylinder in Paris, no longer exactly equal to a kilogram. But you can't redefine the kilogram in isolation because other base SI units depend on it. Take the mole, for example. Currently, the mole is defined as the amount of substance that contains the same number of particles as there are atoms in 12 grams of carbon-12. That's Avogadro's constant. And it depends on what 12 grams is, which depends on what a kilogram is. So again, Avogadro's constant currently has some uncertainty. But after the vote, the plan is to fix Avogadro's constant to be exactly this number, in such a way that it is internally consistent with the new definition of Planck's constant. There's a direct relationship between Avogadro's constant and Planck's constant. Likewise, the ampere will no longer depend on the kilogram. Instead, it will be defined based on this newly fixed value for the charge on an electron. And the Kelvin will be based on the newly fixed Boltzmann constant, which relates the temperature of a gas to the average kinetic energy of the molecules. And this will be its exact value with no uncertainties. Now, will these new definitions change anything? Well, for most people, no. I mean, your food is still going to weigh the same, as are you, and temperature is still going to work the same way. You know, everything basically stays the same. And that is as it should be. The point of this definition change is not to shake things up, but to keep things consistent and reliable forever. All we're doing is removing the dependence on a physical object, which theoretically at least makes it possible for anyone, anywhere to make incredibly precise measurements. Now, I should point out that a volt will actually change by about 1 part in 10 million, and resistance will change by a little bit less than that. And that's because back in 1990, the electrical metrologists decided to stop updating their value of effectively Planck's constant and just keep the one they had in 1990. And there was a benefit to that. They didn't have to update their definitions or their instruments. But now that we've realized that Planck's constant is actually slightly different than the 1990 value because of better measurement techniques, well, now the electrical metrologists will have to change. But that's a very tiny change for a very tiny number of people. I think they'll be fine. You know, I've been trying to ask myself the question, why am I so interested in this topic? I mean, I made like 4 videos on it. And the reason is, you know, to me, the world and the universe is a big, complicated place. And when we're actually able to ascribe numbers to it, it's like we are wresting some sort of order out of the chaos that is our universe. And that is the beginning of our understanding of the way things work. You know, measurements are the foundation of science. They allow us to make observations. I think it's no surprise that, you know, Kepler was really able to figure out what was going on with the planets, that they were actually moving in elliptical orbits, once Tycho Brahe had made the most accurate measurements of their positions that people had ever made. I mean, I think that's no coincidence. And if you look at the discovery of the Higgs boson at CERN, or the detection of gravitational waves, these are, in my view, the pinnacle of human achievement. I think they're orders of magnitude greater than the achievements that we make in literature and art and fashion. And I don't say that to disparage those disciplines. I know that they're hard, I know they take a lot of human brain power, and I'm not saying scientists are smarter, but the tools that scientists work with and the system in which they work is what allows them to make such great leaps, because science builds on itself in almost, an exponentially improving way. And that, to me, is why this is so important, is because it allows us to take our measurements to the next level. No longer are we bound to physical objects. I mean, face it, up until now, we've essentially been doing a glorified version of Indiana Jones. Now, we are taking that next leap to the abstraction that all of our units are based on the way nature is and the way the universe is. We're no longer tied to physical objects.
So how do we look at units? One of the first things we can look at is scientific notation. This employs powers of 10 to describe really big or really small numbers. So for example, 10 is 1 0, 100 is 2 zeros, 1,000 is 3 zeros. So we can write this in terms of the decimal place behind that quantity number. So 5,000 can be written as 5.0 times 10 to the 3 because we moved over 3 places.
In order to write these numbers in scientific notation, they need to be in the form of A times 10 raised to the power of B, where A, called the significand or mantissa, is greater than or equal to 1 and less than 10. So to rewrite 15,600,000 in scientific notation, we first need to determine where we'd have to place the decimal in order for A to satisfy this condition. Right now the decimal point is here, and in order to satisfy this condition for A, the decimal point would have to be placed here. Now by counting the number of decimal places from here to here, we can determine the exponent on 10. So we have to move it 1, 2, 3, 4, 5, 6, 7 places to the left in order to satisfy the requirement for the value of A. Therefore, written in scientific notation, we would have 1.56 times 10 to, we move the decimal place 7 places to the left, so our exponent will be positive 7. Now sometimes it's difficult to remember whether this exponent should be positive or negative, and here's an easy way to remember. If we start with a large number, like we did here, 15,600,000, in order for this to equal a large number, this exponent here will have to be positive. Multiplying by a positive power of 10 will make 1.56 larger. Now let's convert a small number to scientific notation. Again, the first step is to determine where the decimal point would have to be in order to satisfy this condition here for A. So the decimal point would have to move from here all the way to here to make 8.72. Now let's count how many decimal places we have to move from here to here. It would be 1, 2, 3, 4, 5. Which means in scientific notation, this would be equal to 8.72 times 10 to the, because we move the decimal to the right, it's going to be negative 5. Again, to me, moving right and left gets confusing as to whether the exponent should be positive or negative. If you can just remember that the original number was very small, then multiplying 8.72 by a negative power of 10 is going to make a very small number like we started with. We want to rewrite the following numbers written in scientific notation in decimal notation. To do this, the exponent or power on 10 tells us how many places to move the decimal and in what direction. So for this example, we're going to move the decimal point 6 places to the right because it's a positive 6. In this example here, since the exponent is negative 4, we're going to move the decimal point 4 places, but this time to the left. The way I remember which way to move the decimal is, if we multiply a number by 10 raised to a positive power, the number is going to get larger. So to make this number larger, we would have to move the decimal point to the right. On this example, if we multiply a number by 10 raised to a negative power, the number is going to get smaller, and therefore the decimal must move to the left. So we'll start with 7.85, and then we're going to move the decimal point 6 places to the right. So we start here, 1, 2, 3, 4, 5, 6, and we have to add zeros into the missing digits. So we're going to have a 0 here, 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 and here. So written in decimal notation, 7.85 times 10 to the 6th would be 785 with 4 zeros. So we have 7,850,000. For 1.6 times 10 to the negative 4, we start with 1.6, and now we're going to move the decimal point 4 places to the left. So 1, 2, 3, 4, and again we must replace the missing digits with 0, so we have 1, 2, 3 zeros. So 1.6 times 10 to the negative 4 would be 0.00016, and sometimes you'll see textbooks put a 0 in the ones place value, which obviously would not change the value of this decimal. So we have 16 hundred thousandths.
We can think of 10 to the 3 is 1,000, 10 to the 6 is million, 10 to the 9 is billion, 10 to the 12 is trillion, and so on up the scale. We can also move down the scale. 1,000th of a quantity is 10 to the negative 3. 1 millionth is 10 to the negative 6. 1 billionth is 10 to the negative 9. This helps us make calculations and use standard units that would be a bit difficult if we had to write the numbers out all together, especially when dealing with really large or really small numbers. But this is something you need to practice and you need to know very well, because it's going to come in with many of the problems you do in the labs, in the exams, in your homework. It's a fundamental aspect of physics that you need to master. We also need to know how to convert between the different units. And there are different ways we can do that and different examples of how we're going to show the ways you can do that. Unit conversion can be very tricky, because if you're not paying attention, the tiniest mistake can lead to very major consequences. An example of that occurred when NASA sent a Martian probe to the red planet and it crashed and burned. Why did it crash and burn? Because one set of engineers were using US units and another team of engineers was using standard SI units.
What does the French Revolution have to do with the time NASA accidentally crashed a $200 million orbiter into the surface of Mars? Actually, everything. That crash happened due to an error in converting between two measurement systems, US customary units and their SI or metric equivalents. So what's the connection to the French Revolution? Let's explain. For the majority of recorded human history, units like the weight of a grain or the length of a hand weren't exact and varied from place to place. And different regions didn't just use varying measurements, they had completely different number systems as well. By the late Middle Ages, the Hindu-Arabic decimal system mostly replaced Roman numerals and fractions in Europe. But efforts by scholars like John Wilkins to promote standard decimal-based measures were less successful. With 250,000 different units in France alone, any widespread change would require massive disruption. And in 1789, that disruption came. The leaders of the French Revolution didn't just overthrow the monarchy. They sought to completely transform society according to the rational principles of the Enlightenment. When the new government took power, the Academy of Sciences convened to reform the system of measurements. Old standards based on arbitrary authority or local traditions were replaced with mathematical and natural relationships. For example, the meter, from the Greek word for measure, was defined as 1/10,000,000th between the equator and North Pole. And the new metric system was, in the words of the Marquis de Condorcet, for all people, for all time. Standardizing measurements had political advantages for the revolutionaries as well. Nobles could no longer manipulate local units to extract more rent from commoners, while the government could collect taxes more efficiently. And switching to a new republican calendar with 10-day weeks reduced church power by eliminating Sundays. Adoption of this new system wasn't easy. In fact, it was a bit of a mess. At first, people used new units alongside old ones, and the republican calendar was eventually abandoned. When Napoleon Bonaparte took power, he allowed small businesses to use traditional measurements, redefined in metric terms. But the metric system remained standard for formal use, and it spread across the continent along with France's borders. While Napoleon's empire lasted 8 years, its legacy endured far longer. Some European countries reverted to old measurements upon independence. Others realized the value of standardization in an age of international trade. After Portugal and the Netherlands switched to metric voluntarily, other nations followed, with colonial empires spreading the system around the world. As France's main rival, Britain had resisted revolutionary ideas and retained its traditional units. But over the next 2 centuries, the British Empire slowly transitioned, first approving the metric system as an optional alternative before gradually making it official. However, this switch came too late for 13 former colonies that had already gained independence. The United States of America stuck with the English units of its colonial past, and today remains one of only 3 countries which haven't fully embraced the metric system. Despite constant initiatives for metrication, many Americans consider units like feet and pounds more intuitive. And ironically, some regard the once revolutionary metric system as a symbol of global conformity. Nevertheless, the metric system is almost universally used in science and medicine, and it continues to evolve according to its original principles. For a long time, standard units were actually defined by carefully maintained physical prototypes. But thanks to improving technology and precision, these objects with limited access and unreliable longevity are now being replaced with standards based on universal constants, like the speed of light. Consistent measurements are such an integral part of our daily lives that it's hard to appreciate what a major accomplishment for humanity they've been. And just as it arose from a political revolution, the metric system remains crucial for the scientific revolutions to come.
Now let's look at significant figures. What are significant figures? This is something I imagine most of you would have learned in high school, but it's good to review it here.
So what are significant figures? Significant figures, or sig figs, are the digits within a number that help determine how accurate a data value or measurement is. And of course, there are rules. Rule number 1, all numbers that are not 0 are significant. Looking at this first example, every single one of these digits is significant because they are non-zero numbers. Rule number 2, any zeros that are in the middle of non-zero numbers are significant. These two zeros are in the middle of 5 and 8. 5 and 8 are two non-zero numbers, so every single digit counts as significant. Rule number 3, zeros after the decimal are significant. These 3 zeros are after that decimal place, so every single one of these digits is significant. Rule number 4, any zeros and coefficients in scientific notation are significant. Notice we have our scientific notation with something being multiplied by 10 to some sort of power. This 8 and this 0 are significant. Okay, grab a pen, write this down. Do you need a pen? Okay. You can borrow mine. All right, now that you're ready, write this down. Rule number 5, any leading or beginning zeros are not, I repeat, not significant. Looking here, these 3 are leading or beginning zeros. They do not count as significant. Only this 4 counts, so there's only one sig fig. Rule number 6, any zeros in a large number without a decimal are not significant. These 3 zeros are within a large number without a decimal, so they do not count as significant. Only the 4 does. There's only one sig fig. But wait, there's more. When adding and subtracting numbers, you look for the least amount of decimal places. For this first example, your first step is to line up all the decimal places. Notice how 5,004, there is no decimal. However, where the decimal would be after this 4 in the ones place. So since we're looking for the least amount of decimal places, that 5,004 doesn't have a decimal place, so we will round to the ones place. Remember, when rounding to the ones place or rounding any number, you look at the one right next to it to the right, and if it is 5 or more, you round up. Your final answer will be rounded up to 5,488. We have 4 sig figs. Moving on to multiplication and division. When multiplying and dividing, you look for the least amount of sig figs. Your first step is to figure out how many sig figs there are within each number. Notice that there are 3 sig figs in this first number and 6 sig figs in the second. So we will round to 3 sig figs. After multiplying, you then want to go ahead and stop at this 0. So you remove that decimal place, and there really only are 3 sig figs. Because of that last rule, this 0 does not count. There is no decimal place. It's within a large number. Only these 3 count as sig figs. It's time to check yourself. Go ahead and try these practice problems. All right, let's recap what we just learned. Significant figures are the digits within a number that help determine accuracy. The 2 rules that you gotta know. Any leading or beginning zeros do not count as significant. Any zeros in a large number without a decimal are not significant. When adding and subtracting numbers, you look for the least amount of decimal places. When multiplying and dividing, you look for the least amount of sig figs.
In this lesson, we are going to look at atomic mass units in more detail. Before we go any further, you will need to be familiar with the parts of an atom and the terms used, in particular, the mass number. You may also wish to refer to our lesson on radioactive isotopes. As a quick reminder, here is a helium atom. It has 2 protons and 2 neutrons in the nucleus. This gives it a mass number of 4. This actually means it has an atomic mass or relative isotopic mass of 4. But 4 what? The clue is in the name, relative isotopic mass. It is a unit of measurement that is based on a comparison to something or in relation to something else. That something else is a neutral, unbound carbon-12 atom. Scientists had previously attempted to use hydrogen and later oxygen-16 as a reference, but as heavier elements and new isotopes were discovered, it resulted in physicists and chemists disagreeing on masses. In 1961, scientists eventually agreed that a carbon atom, or to give it its full and correct name, a carbon-12 atom, has a mass of exactly 12, making it the accepted reference atom. In fact, the mass of a carbon-12 atom is so exact and well agreed that it is sometimes written to 4 decimal places. Therefore, one atomic mass unit, or AMU, is quite simply 1/12 of the mass of a carbon-12 atom. Every atom has its own unique atomic mass based on this relative scale. Our earlier example of helium had an atomic mass of 4. In full, this means that the helium atom has a mass of 4 times 1/12 of the mass of a carbon-12 atom. Of course, it's far easier to write this as 4. Following this rule, a hydrogen atom has a relative isotopic mass of 1, and a fluorine atom has a relative mass of 19. Now it's your turn. What about nitrogen? Here's the atom. Now pause the video whilst you work it out. All we need to do is look up the mass number for nitrogen. It is 14, which means the relative isotopic mass of the nitrogen atom is 14. And that's it. Now, some of you may have noticed that not all atomic masses on the periodic table are whole numbers. We'll be covering these in our lesson, Why Aren't All Atomic Masses Whole Numbers? But from this lesson, you need to remember one atomic mass unit is 1/12 of the mass of a carbon-12 atom, and we can use this to work out the relative mass of a particular atom.